Hello there. Good morning, everyone. So today we are going to start lecture number 9, surface integrity. It is a module on surface integrity in grinding. This is lecture number 9.1. So what is surface integrity? Let us try to understand that first. Surface integrity is not like grinding force, grinding temperature. It is neither also like grinding ratio. It is a combined characteristics and it is a combination of property of the material after it has been ground. What kind of properties? Surface and near surface characteristics. As far as surface characteristics are concerned, you can say surface roughness. Nowadays both 2D and 3D surface roughness are being used. So you must be knowing something like RA, RZ, RTM and all that. So these are 2D surface roughness characteristics. Nowadays 3D surface roughness characteristics like SA, that means all of their equivalent, instead of measured along a line, they are measured over a surface. So these kind of surface characteristics. Microstructure. Upon grinding, is there any change in the microstructure of the work material or not? Is there any change in the micro hardness or bulk hardness of the work material or not? You might say, why would it happen? As we know, during grinding, lot of heat enters the workpiece and there is a coolant which is applied. So if the temperature is such, this particular application of coolant and high temperature can lead to annealing, it can lead to hardening, or it can even lead to tempering. So there is a possibility of change of microstructure and change of hardness and micro hardness. The next difficult thing which is very much related to surface integrity is residual stress. And if the residual stress is tensile in nature, it is not necessarily tensile. If it is tensile in nature, then there are problems. If it is tensile in nature, it may introduce subsurface or surface cracks. And if there is a tensile residual stress, there would be loss in fatigue strength. I should not say fatigue strength, it is more like fatigue life. So there would be a loss in fatigue life. Corrosion resistance, that would be impaired or it will go down. Erosion resistance, that will go down. What is the implication of these in mechanical design or mechanical systems engineering? If there is a product, if it is a power transmission shaft and you can see both subsurface and surface cracks, then definitely you are not going to use that shaft in your machinery. How do you reveal subsurface and surface cracks? For subsurface, you may have to go for ultrasonic evaluation or X-ray evaluation, and surface cracks can be revealed by dye penetration test very easily. And if you have very large amount of tensile residual stress, then the fatigue life would be a problem. So most of the time, in case of mechanical engineering, if it is a power transmission shaft which is subjected to both bending moment and shear stress, if its fatigue life is compromised because of high tensile residual stress upon grinding, then that grinding process would not be acceptable. What is the implication of corrosion resistance? Say for example, ocean going or sea going vessels, they would be having their propellers. So most of the ships, they would be driven by propellers. Those propellers would be acting, those propellers, if it is a sea going or ocean going vessel, they have to work inside the water which is salty, as because we know the sea water and ocean waters are salty. So in that salt water environment, the corrosion would be much more pronounced. Similarly, what is erosion? Erosion is removal of material or wear of material because of impact of solid particles or liquid particles. So if an aeroplane is flying over desert, a military aircraft is flying low over our Thor desert or any other desert for that matter, so there the sand particle can come and impact the parts of the aircraft or aero engines. And if that aero engine component is having tensile residual stress, then the erosion resistance would also be a problem. So tensile residual stress is not at all acceptable, or it has to be lowered. Even if there is tensile residual stress, it has to be lowered. If it is not lowered, then there is a problem. One problem of tensile residual stress is subsurface and surface cracks. This is, the work material is high speed steel, so it is a tool steel which has been ground by alumina. This has been ground under dry environment and this has been ground under wet environment. This is around 30 micron. This is around 30 microns. So this much would be more than a micron. So there are rather large cracks which are appearing on the ground surface. Is there any other example of subsurface crack? These are not so wide cracks. This is around 20 micron. The scale bar is 20 micron, which is given here. This particular work material is titanium Ti64. That means titanium, aluminium, vanadium. Titanium 6% aluminium and 4% Ti6Al, 4% vanadium. This has been ground by silicon carbide grinding wheel. Okay. And this has been ground at 30 meter per second, 2 meter per minute, and at 10 micron with ample coolant, with ample supply of coolant. Despite that, as you can see, this is the direction of VW. So this is the top surface. This is your top view. This is your top view. So as you can see, there are micro cracks which are appearing, and most of the micro cracks, they are more or less perpendicular to this cutting velocity vector. That means there must have been lot of tensile residual stress which was induced upon grinding. So this is residual stress, and that residual stress was tensile in nature, that was induced, which led to formation of these subsurface cracks which are shown here. So that led to formation of these subsurface cracks which can be seen here. There are some cracks which are in not exactly perpendicular direction, but most of the cracks are more or less in the perpendicular direction of VW. So this shows how dangerous is induction of tensile residual stress. It leads to subsurface cracks, and once you have subsurface and surface cracks, you cannot use that component for any useful purpose. Just give me a moment. Now let us try to understand what are the sources or origin of residual stress. Not in machining, but in grinding. So what are the origin of residual stress? So there are three origins. One is mechanical, one is metallurgical, one is thermal. First, let us try to understand how mechanical stress is induced. Because of mechanical action, compressive residual stress is induced. What is the mechanical action? Mechanical action is because of cutting action of the grit. So mechanical action is nothing but the cutting action of the grit. So if I go back, okay, this is one. The other one is the metallurgical transformation. If you are grinding steel, then there is a possibility of austenitic to martensitic transformation, because of which compressive residual stress takes place. As we all know, that in grinding, lot of temperature evolves at the grinding zone, particularly within the workpiece. This is the thermal origin, and because of this thermal origin, tensile residual stresses are induced. We are going to cover all three of them, what kind of stress is induced. So let us come to mechanical. So this is your x-axis and this is your depth direction. So this is Z, and here the abrasive grits, they have machined they have ground in this particular path, and as they have ground, the grid tip, if you recall, the grid tip, they have undergone, they have produced some kind of primary rubbing. So that primary rubbing has introduced what is known as plastic deformation within the surface, and because of this plastic deformation, compressive residual stress gets induced. So this is a simulation, this is not a actual experiment. This is a simulation using finite element method, which shows that upon machining, what kind of stresses is induced. So here, as you can see, a completely compressive stress is induced within the surface, and that gradually becomes 0, lightly tensile, and then it becomes 0. Both a 2D simulation and a 3D simulation has been done. That is not important what kind of simulation has been done. What is important for you to know is that upon machining, you induced a compressive residual stress that becomes slightly tensile and then almost becomes 0. So this is the nature of the induction. So what we have said here is that during machining, compressive residual stress is induced. The physics of the process is plastic deformation of the work material because of microcutting action of the abrasive material, and that is shown here. However, this is not for grinding. Please understand, this is for a simulation of micromachining. Micromachining and grinding are very similar, because in micromachining the uncut chip thickness, and in grinding HM, they are more or less similar, though in micromachining it would be 5-6 times more than that. So this shows how compressive residual stress gets induced because of micro cutting action. Now let us come to metallurgical transformation. So these are unit cells. So this is a ferrite, this is an austenite. I'll come to this later on. In case of ferrite, A, B, C, that is this A, B and C, they are all equal, and they are equal to 2.8670 angstrom. What do you mean by BCC? This is body centered cubic. So this is one, this is one, this is one, here you have one, here you have one, here you have one, here you have one, and there are two more atoms which are inside. So here you have one, and at the center, so at the center of this crystal there is one more crystal, one more atom. So this is BCC. This is face centered. In this, at the corners you have 8 atoms. And there is one which I should have shown by dotted. Instead of that, I am using a different color. Other than these 8 atoms, you have few more atoms. Where are they? They are at the face. So this is face number 1, face number 2, face number 3, face number 4, face number 5, and face number 6. So this is BCC. Here also A, B and C are same. Between these two crystals, not only A, B and C are same, alpha, beta and gamma, they are also 90 degrees. See, these are purely cubic crystal. Austenite get transferred to martensite. This you must be knowing. And martensite is a BCT, that is body centered tetragonal. So here you have 1, 2, 3, 4, 5, 6, 7 and 8 atoms, and there is a central atom. What happens? The C value increases. So A and B, both A and B, they are given by this equation, where C percentage is the percentage of carbon, and C value, that is the unit cell along Z, unit cell dimension along Z, is this much angstrom. So this is martensite. So upon transformation from austenite to martensite, it provides a BCT structure where the C along the Z axis gets elongated with respect to A and B. So here this is your A, this is your B, this is your C. So A is equal to B and C is more than A and B. So this is what is the transformation from martensite to ferrite. Austenite to martensite. I have also given you the basic definition of a ferrite. Now the question is how this transformation takes place. This is a complex one. So what I have done is that I have put 3 unit crystals of FCC. Now the corner atoms are this one, which are shown by pink. So corner atoms, wherever you see pink, they are corner atoms. The face atoms on these faces, if the faces are vertical, they are brown. So pink are corner, brown are horizontal face atoms. Vertical face atoms are what? Vertical face atoms are, what is this color? I don't know what is this color. It's this color. And there is also vertical face atoms. This is also vertical face atom. So one is green and there is another color. I do not know. It is kind of blue, marine blue kind of thing. So these are the colors. Now when the transformation takes place, a new unit cell forms by these. So this one, these 4 atoms, and as you can see, this particular atoms gets incorporated. So you have this particular crystal. Here I have used a separate color. So these 2 pink remains. The brown gets green type of thing. So this brown is this one. This brown is this one. And whatever green is having here, that becomes this particular green. So this is austenite. And this is martensite. This is FCC, where A is equal to B equal to C. And this is martensite, where A is equal to B and C is more than A and B. So this transformation takes place, and as you can see, this transformation has been explained here. Some of the corner atoms and face atoms, they form a new unit cell. They change their ABC values. However, C becomes more than AB, and you get this. Now, is it possible to predict, if you know the unit cell dimensions, what kind of compressive stress or tensile stress would be generated? Say for example, this is the volume of the unit cell. Upon transformation, it becomes larger. So if it becomes larger, or if it tries to become larger, what kind of stress would be induced? Would it be compressive stress or tensile stress? This is not a single unit cell. This is surrounded by other cells as well. They are not going to give away. So if it is trying to expand, the existing surrounding unit cells, they would not allow it to expand to such extent. So you want to expand, you are not being allowed to expand. So here, if there is a volume expansion upon transformation, it would not be allowed to expand to its full extent. So try to think of it. There is a free dinner. Unfortunately, your pant is very tight, your belt is very tight, and you have eaten a lot. So what kind of stress would you feel in your belly? It would be a compressive stress. Your belly would try to expand, but the pant, the trouser and the belt would not allow it to expand. So you will feel compression on your belly. So similarly, compressive residual stress would also generate. This is the philosophy. Now, can we do the maths and predict what kind of stress would be generated? So this is FCC. This is a number which I have written as 4. What is this 4? This is the effective atom numbers. How many effective atoms are there? Here itself you have 8 atoms, but each corner atom is shared by 8 surrounding cells. And there are 6 face atoms which are shared by 2 surrounding cells. So it is 1 plus 3, which is equal to 4. So effective number of atoms in case of a FCC cell is 4. In case of martensite, these are the corner atoms. So once again 8 divided by 8, and there is a central body atom. So that is 1, that is not shared. So there are 2. So this is equal to your 2. The effective number of atom in case of austenite is 4. Effective number of atom in case of martensite is 2. In case of Ferrite also it is 2. The logic is same. But we are not concerned about ferrite at this moment. During grinding, what happens? Temperature goes up. So if there is any austenite cell, that will go to martensite, and this if there is any austenite cell formed at the high temperature, when it is coming down to lower temperature, then martensites will form. Typically, most of the steel would be having ferritic structure at room temperature. It may have pearlite, cementite and all those. So those ferrites will transform into austenite at high temperature. Now once the temperature goes down, as the wheel goes out and the coolant is applied, this austenite will transform into martensite. This transformation, I am saying as a fact, that would induce compressive residual stress. But where is the mathematics? Let us see the mathematics. So this is your, just a minute, let me change the color. I cannot see this color very readily. So, oh God, where is it? So this is your austenite values, FCC. So this is the volume, which is nothing but A cube, because A is equal to B is equal to C. In case of martensite, this is A value and B value, this is C value. Let us assume carbon percentage is 1. Then you can calculate A, you can calculate B, that would be the base area, into C will give you this particular volume. So as you can see, austenite to martensite transformation gives rise to reduction in volume. How can it encourage compressive residual stress? So we must be missing something. What we are missing is the specific volume. That means how much is the volume per atom, specific volume. So there were 4 equivalent atoms. So this is the specific volume for austenite, and this is the specific volume for martensite. This is getting divided by 2, this is getting divided by 4. And as you can see, the specific volume has gone up. As the specific volume has gone up, that cell, as because it is being surrounded by other cells, would feel a compressive stress. This is a data, this we have not calculated. This is per gram of austenite, what is the volume, and per gram or martensite, what is the volume. And here also you can see the volume of martensite is more. This calculation I have not shown. I have shown a different calculation just above. So if I tell you that there is a kind of transformation happening because of grinding or any other manufacturing process, and you know the crystal structure and the unit cell, by looking at the metallurgical transformation, you should be in a position to predict what kind of stress would it incorporate. Would it incorporate compressive stress, or would it incorporate tensile stress? So 2 aspects are covered. What are those 2 aspects? One is mechanical, another one is metallurgical. Mechanical is nothing but because of the cutting action, plastic deformation. Metallurgical is nothing but because of change in the volume of the unit cell. The specific volume will change, and when the specific volume changes, either the cell expands or it contracts. If it tries to contract, if it tries to expand, surrounding cells will not allow it to, so compressive stresses will develop. If it tries to contract, surrounding cells would not allow it to contract to the fullest extent, and tensile stress would develop. So this is the basic theory. Now let us go to the last one. This is your grinding wheel. This is rotating in this particular direction, and here if this side has been already ground, your temperature variation would be like this. So this we have done earlier, and on this direction your temperature variation would be like this, where this depth is very low, maybe 0.2 to 1 millimeter or so. It is a very low depth. So this is my workpiece. Now workpiece, what I have done is that I have segmented the workpiece into 2 pieces. The top layer, what is the thickness of this top layer? Thickness of this top layer is more or less equivalent to this. So during grinding, this top layer goes to a high temperature. As it goes to high temperature, it tries to expand from this point to this point. How much would be that expansion? That expansion would be alpha into theta into LW. But this lower material is not basically detached from it. Only for the sake of explanation I have detached it. So what would happen? It would not be allowed to expand to that particular extent. So if it is not allowed to extend to that particular extent, so there would be a delta amount of distance which would not be allowed to expand. So delta by LW would be a strain that would take place. If it was allowed to expand, there would not be any strain. But this is a thermal strain which would happen. Because of this thermal strain, if we assume one-dimensional analysis, this is the stress which will develop, and this stress you are trying to expand, you are not being allowed to expand, would be compressive in nature. During grinding, if this compressive stress is high enough, then there would be plastic deformation. And during the cooling period, this plastic deformation cannot be recovered. And what you would have is that whatever compressive stress develops during grinding, that compressive stress reverses its direction because that plastic strain cannot be recovered and a tensile residual stress is induced. So why tensile residual stress induces? Because your temperature is high. As because your temperature is high, your thermal strain is high. That induces some amount of stress. If that stress is more than the in situ flow strength of the material, there would be plastic deformation or there would be plastic failure. During the cooling period, this plastic failure cannot be recovered and tensile residual stress would be generated. So, what are the issues here? For tensile residual stress, you have something coming from mechanical, something coming from metallurgical, and something coming from thermal origin. This is compressive, and this is tensile. And this is a typical steel which has been ground at high A, and there are two stresses. This is along the direction and this is perpendicular to the direction. So along VW, this is perpendicular to VW. These are the two stresses, and as you can see, the residual stress, the effective residual stress is very, very compressive. So this component of residual stress predominates or dominates everything else. Mechanical can be induced a stress of minus 200 MPa. This can induce a stress of 100 MPa or so, but thermal origin induces very high tensile residual stress, and this is the result of the combined ground surface residual stress. So how do I control it? For controlling residual stress, you have to control the grinding temperature. So when we were discussing grinding temperature, we said that this is the most high grinding temperature is the most horrible thing that can happen to grinding. That has to be controlled, that has to be brought down, and if you can bring it down, you would not have tensile residual stress. And if you do not have tensile residual stress, then expectedly you would not have these problems. This time, typically in other years, I cover the measurement of tensile residual stress or measurement of residual stress. I do not know whether I would be able to cover this in this particular semester or not, because this is a short semester. Let us see how much we can cover. So I'll take leave today. This particular surface integrity is very important in grinding, and it is becoming important even in industry. Measurement of tensile residual stress and control of tensile residual stress, particularly control of tensile residual stress, can only be done if we can control the temperature. So whatever estimation we have learned, so from that lot of control strategies were discussed or identified. So if they are implemented properly, or before doing grinding, if someone can estimate the temperature, then not only he would be able to control the temperature, but also tensile residual stresses would not be induced. Thank you so much. So this is our module number 9, lecture number 9.1. Thank you for your attention.